All right, so this one we're supposed to minimize and maximize the function z subject to the constraints. Well, we have z is equal to 3x plus y, and then we have 2x plus y is less than or equal to 20, 10x plus y is greater than or equal to 36, and 2x plus 5y is greater than or equal to 36. And then our non-zero constraints x and y both have to be greater than or equal to 0. Okay, so that's our problem, and we want to do both minimizing and maximizing this. So first steps is graph the feasible region. So we're going to graph each of these, and we're also going to say it's always going to be in the top right region. So quadrant one. So it's going to be up here. And so when we graph those, the lines actually are going to continue on each direction. But what the regions are that they cross is going to be in this region here. So this region S is actually going to be where the feasible solution is because it's going to be less than this line, greater than that line, and greater than that line. And so that's where we have this S region. So because of this bounded, then we can find both a maximum and a minimum value on S, and it's going to occur at one of the corner points. So we have 3 corner points. So what we need to do is find the coordinates, and then when you do that on your calculator, you're going to have something that really, like I said, it's going to look more like you're gonna have something coming down like this. You're gonna have something coming over like this, and you have something maybe coming down like this. And then this piece is really this shaded piece in here. And so that's going to be kind of where this shaded piece is kind of that piece over there. So because it's going to be less than that line, greater than that line, and greater than that line. So that's why we have something like this for S. Okay. So in our calculator, then we could find the intersection here, we could find the intersection here, and we could find the intersection here. All right, so step two, we're going to evaluate the objective function, which again is this top one, based on each of those corner points. And so our corner points, they were nice. They gave it to us here in the graph. And so we plug them into our objective function. We get 15, 22, 28. So what does that mean? Well, we're supposed to determine optimal solutions that we found here. And so basically the minimum value is what? Well, that's the smallest one, which is 15. That's at 3.6. And the maximum is where? At 8.4, which is our 28. So that's going to be our max. And the other one is going to be our min. So again, we're just looking at our table. That's the max. That's the min, just using this table approach. All right. What about this one? Minimize and maximize this function according to these constraints. So these constraints, we have a couple of different ones. We have this one is y is less than or equal to 20, but here it says x and y both have to be greater than 0. So y basically is going to be, in that up above, but maxes out at that 20. Has to be at the 20s and max, and then we draw those two lines or whatever, and then we kind of figure out where the region is that's a feasible region. So when we do that, there's our 20 line up there, and then we kind of come down here, and the feasible region is in this area, which is again labeled as S. Okay, so again, we can find all the corner points. That's not a problem. And the key difference here is because the x is unbounded, it doesn't have any bounds for x, it just anything greater than 0, it just keeps going on and on and on. That means then there's going to be a minimum value, but it's not going to have a maximum value. So there's not going to be one of these when we get done. It's just going to have one of these. So what we have to do is we have to plug in all those points into our objective function and solve and see what our minimum value is going to be. And so we summarize them in the table here, and our minimum value, it looks like it's going to be 2 points. And the 2 points are down here, the 4, 6, and 16, 0, and that minimum value is at 160. Okay, so that's going to be our solution of the minimization of this problem. Now, again, it's not optimized for maximization because it keeps going, it's unbounded, and so that one doesn't work, and so we don't have to worry about doing anything there. All right, let's stop there.